Good day to Doctor and my team member. Today our group 2 will present about controlling DC motor using PID controller of electric drive subject. Firstly, my name is Balarajan Sanasi and my metric number is CE190056. I will present about the project background of this project. Then, proportional integral derivative controller known as PID controller used in this project, and this system is an important part for controlling DC motor speed controller and also feedback based closed loop mechanism often used in industrial control system and other applications which need constantly modulated control such as cruise control in car that maintains same speed RPM of the car while ascending a hill, closed loop water heating system, AC or DC motor controller in automation. Therefore, a PID control calculates an error value of ET as the difference between desired set point and measured process variable on a continuous basis and perform a correction based on proportional integral and derivative term defined by Pi and D accordingly. In addition, when PID control coupled with motor, it creates a closed loop system. The PID algorithm is calibrated using engineering software such as MATLAB Simulink by adjusting or auto-tune the values of proportional gain Kp, integral gain Ki, and derivative gain that is Kd to produce a desired motor speed which reduced overshoot and extended settling time. After that, for this project we chosen battery drilling machine based on small scale model application, and that is because battery drilling machine need to operate in constant speed when drilling an object. After that, the battery drilling machine used to drill a hole by required to maintain the constant speed when drilling into material, although they consist opposite frictional resistant material. As a result, we model closed loop DC motor speed control using proportional integral derivative known as PID control based on our desired application in MATLAB Simulink software. Next, we chosen series excited DC motor for our model of battery drilling machine and then chosen appropriate DC motor parameters. In addition, we converted DC motor circuit to transfer function block diagram which appropriate parameters to design and simulate in MATLAB Simulink software. In addition, the objective of our project is to design the DC motor speed control using PID controller in MATLAB Simulink based on battery drilling machine application, and also to analyze the performance of speed of the DC motor using proportional integral Pi, proportional integral derivative PID, and without PID controller in MATLAB Simulink, and also analyze the performance of speed of the DC motor by manually performed and auto-tune the PID controller in MATLAB Simulink. Then I will pass the next presentation to my team member. Thank you.
Hello and Assalamualaikum. My name is Nur Izzati binti Omar, CE109111, and I will present about project analysis. For our project, we focusing more the DC motor speed control using PID in this project. We decide battery drilling machine which is operated by the DC motor. We choose series excited DC motor for the battery drilling machine that model in this project, and then we converted the DC motor in transfer function based on plan and process in MATLAB. After that, we simulate various DC motor speed controller using PID controller. In addition, we be able to declare that the proportional integral derivative controller, which is PID controller or term three-term controller is a feedback-based closed-loop mechanism, often used microcontroller by appropriate algorithm. After that, to design closed-loop control system, be able to use PID system in microcontrollers such as PIC.
Assalamualaikum warahmatullahi wabarakatuh. My name is Norman bin Senu, BE30703, and today I will show you our simulation for our project DC motor speed controller with PID. Now, first I will show the subsystem for our control system. Inside the subsystem, there is the DC motor for this project. How we determine this block diagram? This is based on the parameter that we have choose in our project, and this is the value of resistance and our value of impedance. And then the next one is the inertia and B for our project. And the value of K is actually the KE and KT, which is constant and same. So we assume that KE and KT is equal, and we have choose the same value for this gain, which is 0.02. Now we have settled with the DC system, which is the subsystem for this project. Now we will go to our control system for our DC motor speed controller. I have run our simulation. Now we can see this is the input that we need, the desired input, and this scope is used to see the desired input and the actual output of this DC motor. I will show the first one, the subsystem or the DC motor without any PID value. See, this is our DC motor control function, transfer function, and this is our scope 1. We can see that this is the yellow one is our desired input, and the blue one is our actual output. So we can see the difference there. And then we move to the second one, subsystem or DC motor with KP value. So we insert this summing junction because in order to see the actual output and the desired input, we need to have a feedback that will calculate the difference between the output and the desired input. That's why we have insert this summing junction, and this KP1 is our value of KP, which is 3533 value. And then it's go to the DC system, our DC motor, and we can see the output. That is the difference between the first one and the second one. This is why we use PID value in our DC motor. Now we move to the third one. Same as the second one, we have insert summing junction. We have summing junction here, but this one is plus because we need to add the value of KP and the value of KI into our DC motor. That's why this one is plus summing junction, and this one is the plus minus summing junction, because this one is the feedback of our system. And this is our graph. Now I will move to the fourth one. Okay, the fourth one is the DC motor with PID value, but manually. We have choose manually the value of PID for our DC motor. And like the previous one, this is the summing junction plus because we need to add these three value into our DC motor, and this one is the plus minus because this is the feedback loop. And we have choose our value of KP, KI and KD with this because KI is integral and KD is derivative. So we have insert, and it have goes to our DC motor, and this is our manual PID result. Now this is the last one. This is the DC motor system subsystem with the value of auto-tune PID. We have used the real PID, not the gain PID or our manual PID. So this is the auto-tune PID, and with this PID controller, we can get a very stable and efficient graph for our system, for our DC motor. And then this is the final result. This is the graph for this project with the helps of PID controller auto-tune. And for the last one, for the bonus one, this is the difference between the manual and auto-tune PID value. This red one is the auto-tune, and this yellow one is the manual. The blue one is our desired input. So that's all our simulation, and this is actually a simple circuit, but in order to ease the simulation, I have combined it into one big circuit.
Hello everyone, my name is Ishwari Singh, matrix card number CE200095, and now I'm going to explain about the result and discussion. This diagram over here shows a full system for the DC motor speed controller with and without PID controller that our group designed. Okay, this is our first result obtained from the system. This upper part over here is the system without PID, and this is a graph obtained from the scope number 1. Without the usage of proportional integral derivative controller PID to control the DC motor, the output voltage does not reach the max output anywhere close to the step-up signal, so it doesn't reach the output desired, and the wave just rises a bit after some delay and achieves the steady state over here. Okay, next is the system for PID, this one down here, scope number 2, and this is the graph obtained from scope 2, which is result of using PID system by utilizing the proportional gain KP. By using proportional integral derivative controller to control the DC motor, the proportional gain of the DC motor is high, so the wave signal rises and overshoots up to 1.45 volt at peak without any delay, and then it oscillates and dampingly until it reaches steady state within the tolerance band, slightly lower to the step-up voltage value. Next here is a graph obtained from scope number 3 utilizing the proportional gain and integral gain KP and KI. Okay, by having both of these proportional gain and integral gain, the wave signal rises and overshoots up to 1.45, same as the previous KP, without any delay, and then oscillates dampingly until it reaches a steady state within the tolerance band. In this case, it reaches steady state exactly as the step input value, so it reaches the desired value, output value. We compare the graph for different tuning methods for PID system. The first one here is manual tuning, and this is a graph from scope number 4. As we can see, by using the manual tuning method of proportional integral derivative controller, the time rise it took to reach the peak point over here is 4 seconds after the step-up voltage input is given, and then the wave becomes overshoot. The derivative gain KD can be made larger to make it decrease until it reaches the steady state within tolerance band. It will take time to reach the steady state to make it stable, and this one over here it will move on until it reaches the same input as the input voltage value. Meanwhile, for the auto tuning method of PID system, the result proves that it is more efficient through the graph obtained in scope number 5. Then by using the auto tuning method of proportional integral derivative controller to control the DC motor, the signal had no delay to rise, and it rises up to 1.1 volt overshoot after 0.5 seconds. By using the auto tuning method, the signal wave takes lesser time to reach the steady state. within the tolerance band, and the voltage will be similar to the input start voltage given. This simulation result in reducing the overshoot and settling time. Lastly, if we combine both graphs for comparison in scope 6, auto-tuning PID is much more efficient compared to the manual tuning because it has less voltage loss and the time taken to rise and to get the desired voltage is also depending on the tuning method that we choose. Auto-tuning takes less time to get the steady state from within the tolerance band and is considered to be more efficient compared to the manual tuning PID. In the end, we combine the full system simulation, and this is the result from the DC motor system with proportional integral derivative controller. As we can see here, having the PID system to control the DC motor is definitely better than without having any controlling system or PID, because without it, it will result in a huge voltage loss. As for the tuning method, auto tuning method is definitely better than the manual tuning method because it is working more efficiently for the whole system. For discussion, the proportional integral derivative controller PID is one of the most basic and widely used controller for DC motor drive, especially for control loop system in order to control variables like speed, pressure, and temperature. There are three main combinations of value that makes this system: proportional gain, known as KP, integral gain, KI, and the differential gain, KD. Proportional gain sets a bar or boundary of performance for the steady state error within the tolerance band. The current is set to be proportional to the error. If the proportional gain is very high, the system could result to be unstable. But if the proportional value is very low, there will be large input error and be less responsive. Meanwhile, integral gain actually improves the performance of the lower frequency, and differential gain, on the other hand, gives incremental improvement at a much higher frequency for the system. Alright, there are two methods to use proportional integral derivative controller system. The first one is manual tuning, and the second one is auto tuning of PID. Manual tuning of PID is common, but it needs several attempts to get the desired value. This method can be said as trial and error to get the accurate result. Auto tuning method of PID system is much more efficient. We are able to perform a step test and gain the controller response automatically. Once the process is started, the model may not be always accurate, but it certainly brings out the similar value of the output desired for the DC motor system. The method is usually done by simulation in application like Simulink to gain the proper desired value. Next, I will pass to my teammate. Thank you.
Lastly, for our project conclusion, we be able to achieve the objective of this project. We be able to design the DC motor speed control using PID controller in MATLAB based on battery drilling machine application. Moreover, we be able to analyze the performance of speed of the DC motor by manually perform and auto-tune the PID controller. Lastly, for the recommendation, we can suggest this system for DC motor power water domestic pump, and improvement can be made in the control aspect of the purpose system design by convert this system into the microcontroller system. And we need to add filter to eliminate the overshoot voltage or current that prevent damage to the DC motor machine. That's all from us. Thank you.